So today we have David Rousseau. David received his PhD in 1992, so not so long ago, from Marseille, for work done in the Aleph experiment at CERN, at lab at that time. So you were in lab, I think, up to 1996, 1997?
Yes.
Okay. At which point he changed to the starting Atlas collaboration. So this is, 12 years before
yes.
Actually
it was supposed to start in 2005 at the time.
Yes. I remember that shifting. David then joined the CNRS in 1993, had a 2-year stint as fellow at CERN, and then remained in the CNRS, where he's a senior scientist since 2009. So David has been involved and has led many artificial intelligent efforts in high energy physics. So, and this also includes advanced training of people in these areas. There's something I wanted to mention. So between 2010 and 2012, David was coordinator of the Atlas offline software, which sounds like a very technical job of some sort. So this was a critical tool for the Higgs discovery. And there are numbers here that I find mind-boggling. So this software ran through 10 petabytes of data, real and simulated. The software involved 4 million lines of code, was developed by 1,000 people over 10 years. So I'm not sure how many efforts of this scale there are. And that was used by 1,500 to 2,000 people of physicists of the Atlas collaboration. So, and today we have a bit of the history of the Higgs discovery in the context of the artificial intelligence. So thank you very much for coming.
Thank you. Thank you, Guilherme. Thank you for the invitation. It's always a pleasure to come here. And thank you for the nice introduction. Okay, so I would like to start with a show of hands. How many of you who have already trained your own machine learning algorithm, even if very simple, even if it is during the courses? I would say third or fourth. Okay, so bear with me. There will be both things relatively simple and things more advanced in terms of machine learning. So I start with a classifier performance. So machine learning algorithms, so typically if we do a simple case where we have two variables, two populations, and then we want to separate the two populations, and then the algorithm will learn from a distribution to give a high score. If we say we have a signal on background, this is always going to be the case for me. We give a high score to things which is very, very signal-like, so in the middle of the blue blurb, and a very low score in the area which is very background-like in the middle of the red blurb. And then the two dimension is projected into one, and then all the most signal-like is pushed to the right, and the background-like is pushed to the left. Depending of algorithm which is used, the score here between -1 and +1, between 0 and +1, is really an arbitrary quantity, which is just used to rank the example or the event which you have on the left from the most background-like to signal-like. And then if I want to build a sample which is as pure as possible, obviously I will start from the right. I will start with the samples which are the most signal-like, and then I will accumulate my sample integrating from the right. And then doing this, I will build a curve which is called the ROC curve. Or this is the receiver output curve, which comes from electronics, I believe. Everyone calls it the ROC curve. It's everywhere in machine learning because it's a very useful common language to compare machine learning algorithm, to compare classifiers. So algorithms which are able to classify signal background, cats and dog, etc. And when you do this, at the beginning, the vertical scale is the signal efficiency, a fraction of signal you have kept, and the horizontal scale is the background efficiency, the fraction of background which you have kept. And at the beginning, you have mostly reaching signals, so you increase faster vertically than horizontally. And then in the middle, it's 50-50. And then at the end, you recover the background. So the curve rises quickly and then go back to 1. It has to go back to 1 because when you're there, you have integrated both curves completely. And these curves, I forgot to say, they are probability density function normalized to 1. And then, depending on the algorithms, you will have different curves. And an ideal curve would be one where all the signal is there and all the background is there. And then you will go directly here and there. This is the ideal curve. And then a random classifier which knows nothing. In this case, the two curves would overlap, meaning that when you integrate, you will move along the diagonal. Okay? And this will be the worst. And then to quantify this, the fact that the curve, the closer they are from the left top corner, the better. A very intuitive way to quantify it is simply to do the integral. So here comes the name, AUC is area under the curve. Voilà. And you clearly see immediately that area under the curve of a random classifier would be just the half of the square, so it's 0.5. The perfect one will be the full square, which is 1, and then in between, you will be able to quantify how good your algorithm is. So this is kind of common language, but then as soon as you're doing something specific, there are better ways to measure the quality of a classifier. But I will not enter it. When you think about it, what a classifier does when, a reminder that, okay, this example was 2-dimensional, but there can be 10, 50, and even 1 million when you're doing this on an image 1,000 times 1,000. So this, in this multidimensional space, what it does, it compresses the information to this score histogram, which can be called summary statistics, and without any loss of information concerning how different the two distributions are. So we'll come back to this. Very important, there is no miracle. Machine learning, AI does not do any miracle. You have examples of this all the time. And in particular, quite important to us is that when the underlying distributions are known, then nothing beats the density ratio. So suppose here, the small example I've done, where you have a signal which is a Gaussian blurb, and the background which is exponentially falling in both directions. The solid line is the contour from just the ratio of the two PDF. What you can see is that this kind of target is shifted towards the larger value compared to the center of the blue distributions. This is because at larger value the background is lower, so there is a compromise. And the bottom plot shows the ROC curve for various, in this case, boosted decision tree. And what you can see is that they are always a bit lower or equals to the green curve, which is the ratio, doing the ratio of the underlying model. So it's quite important to realize that machine learning is interesting only when there is no mathematical model for the distributions which we are looking at. Okay. Now, the Higgs boson will be quick. So this is the complete scheme of the standard model of particle physics. Sorry. With, on the top, we have let's start with this one. The two quarks up and down. With these two quarks, you do proton and neutron. And then the electron, the lepton. And with these three particles, you do all the matter which we know. There is the electron, which is a very elusive particle, which is the partner of the electron. And then we have three families. We do not know quite why. Then there are the bosons, which are the mediator of the forces. The gluon for the strong force, the photon for the for the electromagnetic force, the Z and the W boson for the weak force, and of course the gravitation is missing here because the gravitation lives in a completely different scientific space. Gravitation is due to the in general relativity to the distortion of space-time, and how to have a gravitation matches with this is an active topic of research. And finally, we have the Higgs boson, which is not a mediator of a force. It's part of the mechanism of the Higgs mechanism, which is responsible for the mass of the particles, the mass of the fermions, but also of the bosons. So this is an example of evidence of the Higgs boson. So this was Higgs boson was proposed in 1964 by Peter Higgs, François Englert, and Brut, I forgot his first name. Brut, which is a partner from François Englert, but unfortunately he is deceased before the Nobel Prize. And so we announced the discovery of the Higgs boson in 2012, the 4th of July. I'm part of ATLAS, one experiment at the Large Hadron Collider. And this is an example of what we see. So that's we have proton colliding at high energy in the middle of the detector. There is a kind of fireworks in all the directions, and energy deposition measured in different parts of the detector. And then we reconstruct all that. We put everything together to understand which particles have been seen, which energy, and then try to infer what has been happening in the middle. And here, this event is the case of a Higgs decaying into two quarks BB, and a W in a muon and a neutrino. And this record, we call this an event. An event is everything we record in a proton collision. And to give you an idea, an event is 1 megabyte. So it's really in terms of size like a picture on your phone. And we have in 1 year nowadays more like 10 billions of such events. So a lot of data to analyze. Okay, of course we've discovered Higgs now 13 years ago. What we have been doing and we still do and we will do in the future is study in very close detail what are his properties. One example why it is important. This is a plot of the stability of the Higgs field, the stability of the vacuum as a function of two particle masses. The top, which is the heaviest quark, and the Higgs. And what things rather strange which has been discovered is that this region is where the field is stable, so it's the field which is everywhere in the universe. And the yellow part is where it's unstable, red part is where it's unstable, and the yellow one where it's metastable, a bit like water which is below zero, and then anything can you shake the recipient, and then suddenly the water transforms into ice. And this could be something which could be happening somewhere in the universe. So it is a bit strange to see that there's a kind of fine-tuning of the parameter to be just at the edge of these distributions of this region, which is quite strange. So it's quite important to pin down these values, and there are other properties which are quite important to measure to make sure that what is the physics beyond the standard model. Okay, and one way the Higgs physics has used machine learning in the beginning of data taking at LHC, so here is 2015, which is to use a classifier, as I just said, by running a BDT, so boosted decision tree, which is a simple one, but quite a robust classifier, on a dozen of high-level features of the event, on the electron momentum, some shape, etc. And this is the distribution of different backgrounds, and the point is the data, and the horizontal scale is the output of the BDT, which I have mentioned before. And the evidence of the Higgs boson is this excess of event in the largest bin. And you can compare this to another channel, which is the Higgs to 2 photon, where it manifests itself directly in the mass, invariant mass, in relativistic meaning, the invariant mass of the two photons. And there you see invariant mass is as 125 GeV, which now we know is the mass of the Higgs boson. And here the evidence for the Higgs is much more direct, because this is recent data. At the beginning, 2012, it was, okay, you really have to squint your eyes to see the bump, but now there is no doubt that there is a big bump here, and a bump in a variable which makes complete sense in terms of physics. While this variable, this classifier output, is much less direct. So this is a challenge of using machine learning in Higgs physics, is that you have to convince yourself, and then you have to convince your peers that you know what you're doing. Okay, and this shows, when I was talking about convincing your peers, so I was working in this paper here, Higgs to Tauto, the one corresponding to histogram which I have shown. And so we are using machine learning, and then the way it works in a big collaboration like that is that there is a review committee, which is called an editorial board, which does its job, is rather conservative. And then when you come with a new technique, they ask for checks, cross-check, etc. And here, and this time, they really asked to do, okay, this is very nice, your newfangled thing, but you should really try to redo the analysis with standard method without machine learning. So we did this, and then the results was consistent with our measurement and less precise. Okay, and we could quantify this in terms of the sensitivity, in terms of sigma. So sigma is the standard deviation. So when you have 2 sigma sensitivity, you expect to be wrong 5% of the time. 3 sigma is 0.1% of the time, etc., etc. So the larger this value, the more sensitive is your experiment. And then our experiment was at 3.5 sigma compared to 2.5 without machine learning. And you can compare this to what you get if you increase the data set by 85%. And it turns out the same story happened in other analysis in my collaboration Atlas, and the same story was happening also in a CMS collaboration. Those are the two other papers here. And it means that in this set of papers, you have really the same analysis, the same everything, and then you have the two results you can compare. It's impossible to do any comparison otherwise, where the data set is not quite the same, the methods are not quite the same in terms of selection of data. Here it's the only papers where you could do this comparison. And at the end, you see some improvement, which is we did not quite understand why it was 125 in some case and 15 in some other case. But what we can do is just take the median and say, okay, in general, using machine learning, even a simple one, the BDT, is equivalent to have 50% more data from the Lâché. And then if you say, okay, the CERN runs the Lâché, the budget of CERN is 1 billion euro per year, you could quantify this improvement. It would be a bit naive, of course, to do this. Okay, this is an aparté. In fact, it's if you interest yourself in machine learning, AI, and so on, you hear stories of going back in time, starting with Turing in 47, I think. And so I did some research, and when looking at the references of papers and looking who was reference and going back up the trees of references, I found this paper by this guy, Bruce Denby, turns out he was postdoc in what was my laboratory, former name of my laboratory, but it was just by chance. And he had graphs in his paper. He was using neural net for tracking and for calorimeter. And I've discussed this, I've shown this in many workshops, etc., and nobody has challenged this, that this was really the very first paper using AI, we can say that, on high energy physics data. And then there was a brief burst of activity with neural net in the beginning of the 90s, and then a few papers, but this died out. And if you hear stories by the pioneer of machine learning, they tell you about the winter of AI And this was the last winter of AI in the 90s, basically because things was not working too well. And plus, there was some theoretical proof that that neural network could not be trained correctly. It turns out it was not true. Plus, there was a lot of tricks found to have a better training, like a standard stochastic gradient descent, for example. And then there is a new burst of AI starting 2012. Okay, this is for history. Now I move to something much more recent. In fact, was published just before Christmas, which is more advanced machine learning, which is Simulation Based Inference for off-shell Higgs. Okay, so this is a very specific study where we look at a decay of a Higgs to 2Z, and this has a very, very interesting particularities, which is like, so these are Feynman diagrams which you read from left to right. So you have the two gluons which are in the proton which collides, which creates through an intermediate triangle the Higgs boson, which decay into Z. That's one diagram. This is the signal, what we want to measure. And the background, also you have the two gluons with an intermediate feature, produce again the 2Z. And then you see that you have the same final state and the same final state. And in this case, the two diagrams interfere. So you are probably familiar with interference in the case of the Young slit diagrams, experiment, sorry, where the light is scattered by two slits, and then there is an interference pattern. Okay? And in particular, suppose you close the second slit, then this point here has some light, but then when you open the second slit, even though you allow more light to come in, the interference is such that you see less light in the place where there is a dark pattern. Okay, so this is a classical case, and here is exactly the same thing. The two diagrams interfere, and they interfere negatively, so that when we have more signal, turns out that this term here is negative, and we have less signal. And this is what we get. So the red line is the background, which is very high. The dark one is the signal, if there was only signal and not the background. And the blue is what we should measure, which is a deficit of background. So the signal manifests itself as a deficit of background, which is very, very unusual and very strange, and we didn't know quite how to handle it. And then we could rewrite this formula here this way, where mu, I should have said, very important, you will see this all the time. Mu, because this the signal strength is something which is 1 if the standard model is valid, and then it just scales the signal by mu. Okay, and we could rewrite the yield, so the amount of events which we have with these three terms depending of mu, and you see there is a term with the square root of mu in addition to the usual term of mu. And then the three terms correspond to three different processes. Okay. So as I said, the signal appears as a dip. So if there was no signal, we could see this amount of event. And then if we increase the number of signal, we have a dip, and then it goes back. Which means that if you measure something, for example, at 1.05, you don't know whether the signal is at around 0 or the signal around 1.5. And this will cause our system to have two solutions quite often, as we will see in a few minutes. Okay, statistical framework. So I like to say that, like you I've learned about special relativity, general relativity, quantum physics, but the thing which I do every day, this is probability statistics. Okay, I don't do every day advanced relativity. It's always about statistics at the end that what matters. So we can write that the probability to observe, to have a data set D when I do the experiment. So it's a probability to have D given mu. So mu is my parameter of interest. I am saying, okay, I only want to measure the signal, the amount of signal, and I conveniently normalize it to the standard model. So mu is 1 if it's what is expected, but I want to measure it. So the probability to have D given mu is first there is a Poisson term, which is the amount of data which I have, and then there is the product of probability for all the events which I see. Xi is the list of features of my event. So you can see this like Xi being the columns of a tabular data set with maybe 10 features or much more. And then I have the lines are all my events. So my probability is this. So the product of the probability for each event times the overall normalization. And the same thing now for the likelihood. The likelihood is the same thing, but now I invert it. So a probability of mu given the measurement of mu given the data set. And the Poisson term has been expanded. And it's very convenient to do the negative log likelihood because they are all products. And we are using the Neyman-Pearson lemma, which is that optimal test statistics is to look at the ratio of the likelihood, which I've just mentioned, divided by likelihood for mu hat. Mu hat is the value which minimize my likelihood. And the tricky thing here is that quite often there are two possible values for mu hat. So T mu, this is the thing which we call the test statistics, is what I want to minimize. So in the classical histogram method, which I've shown so far, we have high dimensional data, and then we manage to reduce it to just one dimension. And then to have one output, one histogram. In practice, it could be a collection of histograms, but a few. And then this histogram is fitted with a sum of background plus a signal. And this is fit with so these immediately recognize these are Poisson law. When you take the log, is quite convenient law. This is the sum of the bins of these histograms. I have, I don't know, 10 bins or 12 bins. Sum of the bins and the amount of data in each of the bins. And this is the inference, the likelihood which I need to minimize. This we have been doing for 10 years. And now what we want to do is something more involved, is that we have still the parameter of interest is mu. And then we use neural network to evaluate I will detail this, evaluate the probability per event. And now my likelihood here, there is a sum, but the sum is on each event. So we have 2,000 events. This is the sum of 2,000 events of the individual probability. So this is quite different. It's unbinned likelihood fit, which is relatively commonly done when the model is simple. But to do this when you have neural network involved, because there is no obvious model to model your data, is new. So I detailed where the probability. So again, probability to see x. So xi is my event. So my event in my parameter space, which is 10 dimension, 12 dimension. My event comes at as a specific place, specific set of value of x. And then this is my probability, is a sum of different processes contributing to this parameter space. This is taken from simulation. So simulation has a bigger role. That is why it's called simulation based inference. And then this function of mu is taken from theory, as it will be clear later. And then to make it easier to evaluate, we divide this by a reference data set, a reference probability, the choice of which is a bit arbitrary. In practice, are some which works better than others. And now this is my final formula. And then this is still quite general and quite important is this ratio is where the neural network will be. This is a ratio of density, and this neural network can evaluate very well. And in practice now for our cases, we have different processes. We have different formula, which I've shown already, which comes from the interference pattern. And now I am able to write the full formula for the density ratio for my event. The very important thing is that doing this, I managed to have mu outside the neural network. The neural network do not depend of mu, and this is quite important because some people have tried to have the mu inside the neural network, and it kind of works, but in practice it's very difficult. It does not. In practice it does not. I will show why. So it's quite important to be able to write this function where the neural networks, the three neural networks there, are computed independently and independently of mu. Okay, so how do we derive this density ratio with neural network? We have data set which is tabular. It means that there is 13 features, long list of events per data set. These features, they are kinematic features from the funnel states. The funnel states there are 4 leptons, 2 jets, and then there are angle between the lepton, invariant masses, etc. These have been optimized in the past. And then neural network will just be classifying, really a simple classifier class between the process of interest and the reference data set. And at the end, this is the definition of neural network. So this is a dense neural network with 5 layers and 1,000 nodes. So this is relatively big. It uses a binary cross entropy loss, and to make sure it is well calibrated, more on that later, we actually use 50 different neural networks which are trained the same way with different random seed to have a result which is much more stable. And then we get a probability, and then by this simple, a very simple play dividing by PRF on both sides, up on the top and the bottom, we get this density ratio. And there is one important step, which is the calibration, because now we don't have a score, which at the beginning I said the score was an arbitrary variable to be able to rank my event from the most background light to the most signal light. Now the score becomes a probability, a proper probability. So now, how do I make sure that I have a proper probability? The simple example is a meteo. So on your meteo app, you have the probability of rain for every day. Okay, 7%, 8%, 4%. And the question that suppose you write down every day the probability of rain for the next day, how do you know at the end of the year that your application was correct, calibrated? It's relatively simple. You group for example, if this was only 10, 20, 30%, you group together all the days where the probability of rain was predicted to be 10%, and then you count the number of times you had rain the next day, and then you have an actual measurement of the probability of rain. And this, you do it for every value. And this, you have curve like that. So this is not obtained from the left. Maybe I should manage to do it. This is the curve I pulled from the web. But then you have a curve like that, which does not work too well, while the curve which you want is a curve which is on a diagonal. That if you predict 10% of rain, then actually the probability to have rain is 10%. And etc. There are different ways to do calibration. One last thing about probability calibration is one really has to realize it is really a different axis compared to the accuracy of neural network. When you start to learn more about machine learning, you have tutorials and etc. The emphasis is always on accuracy. Okay, the calibration is always on second thought. And it's quite important to realize that this is different, because suppose that the probability of rain in Lisbon is, I don't know what, 15% the whole year. My application here could say, okay, probability of rain 50%. And then I'll try to see whether it's well calibrated. At the end of the year, I will find, yes, of course, 15%. So it's well calibrated, but it's quite inaccurate, because, of course, you want to do better than that. So it's quite important to realize that the accuracy is really different from the probability. Okay, so this is what we do for the calibration from our neural network predicted score. And we have these curves, this accuracy curve, which works quite well. And the second check, which is very useful, is that since we have the ratio of density, I can start from the, so this is in the blue. The blue is the distribution distribution for the signal, and the green is distribution for the background. You can hardly see it. And then with the density ratio of S over B, I can transform my signal, B over S, transform my signal into my background. And this is S over B reweighted, and it matches exactly, which is a proof, similarly to the example I gave with the Meteo, is a proof that my density ratio was correctly estimated. Voilà. Then we do a negative log likelihood fit. So this is a very classical statistics operation. Usually it looks like that. It looks like a parabola, because it's because of this Wilks theorem says that at the limit a negative log likelihood fit is like a quadratic chi-square fit. So you have a parabola, but in our case it's clearly not the case. So we can ask ourselves, okay, are we at the limit of Wilks theorem, at the asymptotic limit? So we have to check that. In particular, because the confidence interval we are going to quote is where the line here crosses the one value at 1 for 1 sigma, value at 4 for 2 sigma. And if we are not at the limit, this will not be correct. So what we do pseudo experiments, meaning that we have 10 million of simulated events. And from these 10 million events, we are pulling randomly 2,000, which correspond to what we are going to have on data. And this we call a pseudo experiment. It's like if there was a parallel universe where everything is the same, and then we want to see the different measurements. And then we do the fit, and one line corresponds to one of these fit. And what you immediately see is that there are different shapes. There is this line here, which is just increasing. And then there are some lines which have a minimum at close to 0, and then a second minimum at some larger value, while some others start at high value. Okay, there are different patterns, which makes it quite difficult to understand. And so to calibrate the line, to calibrate these two lines, what we need to do is called Neyman construction, where basically we simulate experiment with mu equals 1, and we plot the values which we get where the different experiments cross this value mu equals 1. And this is what we have. You see the peak here at 0 corresponding to this big peak of minimum at 0. Then we integrate from the left. We stop when we have 68%, which is the standard 1 sigma deviation, or 95%, which is standard 2 sigma. And you see it's not quite at 1, not quite at 4. And we do this for different value of mu, etc. And at the end, this is what we have. These curves correspond to the correction from the Neyman construction. So then when we quote the confidence interval, we don't quote the confidence interval with respect to this line here, but with respect to the corrected lines. So this was a good 6 months of work for my student to have this. Also because doing this is very efficient to find bugs. There was a lot of cases where the neural network was not quite well calibrated, or there was some other issue, and then these curves was just going to the sky, So this is another reason to why it's good curve to do. Plus, it was very useful to convince our colleagues that things was well understood. In particular, because on the right you have the same thing done by our colleagues on the histogram-based analysis using the classical approach, where you see the curve is really similar, which means that the correction does not come from our techniques. It's really fundamental to the interference pattern. I think I'm going to skip the interest of time systematic uncertainties, just to say we take into account nasty effects like all the interaction of particles in the after they've been created, interaction of particles with the matter. We take this into account properly, and voila. So then this is the measurement which we get. The measurement is the intersection of this line with this Neumann construction, and then we quote this confidence interval. And then this is the measurement. So this is not yet an evidence for this process, which is an important measurement to do. But given we're going to have in the next 10 years something like 24 more data, 20 times more data, we're confident we're going to measure this. Voila. So this is the conclusion of this part. So this is the first implementation of neural simulation-based inference. In the past, there was a lot of proof of concept. Then it was quite a lot of work to make it work for real in a real analysis with all the nasty details. And there was 2 papers published, not published, well, submitted and published soon. And this proves that an SBI is really a method which is relatively complex, but well adapted when there is a non-linear impact of the parameter of interest. It's not something we recommend for a more classical cases. Okay, I have 2 smaller topics now. One, this is the competition I've been working on with another student, which is that how to address uncertainties. So in general, we have a machine learning method in HEP which are trained on simulation, where there is a systematic uncertainty, systematic uncertainty. For example, the calibration of measurement of some particle is not quite correct. And then we want to know, okay, when we apply it on data, we don't know the Z, so Z is a systematic effect, and then what is the impact of it? And what is traditionally done is to do experiments, as I've shown, where you change Z and you see the impact on the results. And what we want to do is to do things more involved, and in particular to take into account the Z at the level of training. So it's called uncertainty-aware machine learning. It's a subfield on its own. An SBI is one of the approach. There are other approaches, but the problem is that it's a typical problem in this case. Each paper says, okay, my algorithm works very well on my data set, and then it's hard to understand whether there is progress or not. And for this, we have organized a competition. So this is started machine learning in high energy physics by doing a competition in 2014, so 10 years ago, a bit more. And this was just a classification problem, similar to the first histogram I've shown with the BDT, with no systematics. And now we have repeated it with first with a lot of data, because we really want to measure very accurately the systematic effect and how well the algorithms are doing. And then there are different systematics on the scale of the tau of the jet, some noise, normalization of different background is a very typical problem. And then what we do is that, okay, we want the person to be able to do a measurement on a pseudo experiment given again the true signal strength, the same definition which you had before. And instead of giving just a value, we don't care about the value, we want to have a confidence interval, okay, a range. And then we are going to evaluate this confidence interval. And here in this case, there is no fancy interference, it's completely linear. Then we build pseudo experiments. So same story. We have a parent master data set. We build a pseudo experiment with different values of the nuisance parameter and of the mu. Okay, so we're doing this regular test. And we then measure the coverage, meaning that each experiment will say, okay, the confidence interval, this line, each segment here is the confidence interval, is one pseudo experiment. And then, for all the pseudo experiments for this configuration, you can see how often the red line, which is the true mu, crosses the confidence interval. And then this should be 68%. And by I, the one on the right is clearly less. And then the score at the end, we want to combine two things. The confidence interval should be as small as possible, meaning the method should be as precise as possible, and it should have a good coverage. So the standard confidence interval coverage should be 68%, which is one standard deviation. And if it's larger, then there is a penalization. Okay, so this is what we have set up. This was quite some work because there is a lot of pseudo experiment to run. So we are it's a project with Berkeley where they have a supercomputer which we've used as a backend, and Codabench is a platform to run different competition. And there was quite some technical work to connect together. This is at the end we have a leaderboard with the score which I just mentioned, the average interval, the coverage. And okay, this is not yet a conclusion because the competition has finished less than 2 weeks ago. And we were an official NeurIPS competition. NeurIPS is a major machine learning competition, so this has attracted quite some interest. But right now we are analyzing the submissions, and we have a workshop on that in May, so we hear more about it in the coming months. And we are already working on a similar challenge, but this time on cosmology, on measuring weak lensing. I will not detail this. And finally, on simulation. So simulation has a very, very big roles and even more bigger roles. And the thing is that the current simulators are quite sophisticated. They have been developed over literally 40 years at least. And, but they are slow because they are complex. And we are going to have more data, so we're going to use more simulation, and we cannot cope with that. So we need to use generative model to help us with that. So you all know now about generative model. You're not impressed. So here you can generate a face, a credible face of a celebrity. And you can, one important is you can change the parameter. Change the parameter like the age, the bird, the smile, and so on. So we can, looking at this, we think we can use this kind of technology in a way which is going to be clearer in a minute. So one important thing is that in physics we have images, but in fact the images is not the data. So what I have shown already is in fact a representation of the data. Data itself is a list of record of energy in different detectors. It's quite complex. It's not the data. This is, for example, the part in the middle of the detector, where these are all the points measured, and then all the points have to be connected together to find the trajectory of particles. This is in a dune, which is a future neutrino detector. This is, in fact, a 3-dimension, very precise measurement. So again, this is a projection. This is not the data. This is, you might have heard about it very recently, detection of the highest neutrino ever detected in KM3net in the depths of Mediterranean. And what you see here, these are photomultipliers, which are spheres like that, which detects light in all directions. And what is represented is the amount of light detected, and in color is the time coded. Okay, so this is again clearly a projection, and this is not this is not something which data which you can easily put in the same algorithm as you put images, because images is really what has started the deep learning revolution in 2012, analyzing images with a convolutional neural network, because the nice thing with images is that they are not bag of pixels. The nice thing is that using the neighbors, which is in a matrix, which is just finding the element I minus 1, I plus 1, etc., there is some information from the neighbors and from the correlation with the neighbors. This is the way you find the edges, and then from looking farther, you connect the pieces of a face, etc. So images are easy. Tabular dataset is very common. Tabular dataset is really an Excel spreadsheet, and then you want to use the vertical column, the features to predict. For example, here it's the very common Titanic dataset to predict who survives. This is time series, another very common very common case, time series, which is often transformed into a time frequency diagram, because so vertical scale is frequency, horizontal scale is the time. So this is for different birds singing, and this is done because when you have done this, you are back to have an image. And in general, transforming something so that you have an image or something easy to digest by existing machine learning algorithm is the best. So when we don't want to do is to do calorimeter simulation. Calorimeter is the part of the cylindric part which is over there. This is simplified view. And what has been done is to create a common open source data set where electrons hit the calorimeter, which is simplified as a cylinder with multiple parts, multiple wedges and multiple layers. And then at the end, what you want to simulate is everything here, which is all the different layers. And as you can imagine, there are correlations between the layers, and correlation where you can see by eye, in fact, the secondary particles. So this is what you want to simulate. So the beginning of this for simulation, this was the GAN. This was in 2016, and this was the very first papers, and we were very impressed by that. Of course, you are not impressed by that because you immediately see that, in fact, okay, these are not very realistic dogs with two heads, etc. But nevertheless, there was a big. This made a big noise, and then there was a lot of violation of GAN. And the principle of GAN is to have two neural networks. One is creating images at the beginning just from noise, creating random images, and then this one is just discriminating, classifying images between fake and real. And then the two are trained together, and once they are trained, this one is able to create credible images. And so what we have done is we use as a source of real images, or we call these showers in the calorimeter. We use our regular simulator, and then we train our neural network to create these images. And I skip this. More or less, some distributions show that it was kind of working, but not too well. You see in the tails, it doesn't to work. The thing that the GAN are very tricky to simulate, and now it's kind of obsolete. And now the most up-to-date, you can say, algorithm is called diffusion model, used in DALI, for example, where it's quite tricky. The idea is to add noise to an image, and then learn at the same time how to denoise it. And then at the end, you can create credible images from noise. And so can we use it? And the answer is yes. So we have colleagues which have tried to do this. So these are the true images, and then their own images from the algorithm. And you see by eye it kind of work. These distributions kind of work, but not too, at least it works better than before. And at the end, the key thing was to be able to, how do you assess the fact that image like that is are good compared to this one? And this is very not easy, because when you look yourself, you look at the images created by a generative model, you see by eye that there is one more finger on this hand, while when you see these calorimeter simulation, you cannot. So the idea is simple, it's a clever idea, which is to use a classifier to distinguish between the original and the generated images or showers. And then it's the opposite, that if the model is able to distinguish the two datasets, then it's bad, meaning that the best raw curve which you would want to have is the case where the model is incapable of distinguishing between the two sets of images. And then you would have 0.5 AUC. And this is, so then they have done something a bit more sophisticated, and then they have drawn as a function of this value, which is the higher the better, and as a function of the time, because we want, at the beginning, we want things to be faster. And the thing is that the diffusion model are over there. They are the best, but the problem is that they have these repeated steps, which mean they are slower, while there are other models which are not as good, but much faster. So you see there are a lot of papers, proposals to how to solve this simulation problem. So it's really a subfield on itself. And this challenge had a nice role in community building between different groups working on this. And so they have published just last year the final paper, but it's something which is very, very, very active. Well, this is my last slide. Is really that the challenges for AI and ML and Higgs physics is very few. It's really the fact that we have semi-structured data. It's not images, and we have to come up with a new architecture to deal with that. Second thing is to control uncertainties. We are physicists. We pretend we are measuring things, and when we measure things, we want to give uncertainties. This is really the basics of experimental physics, to give a credible confidence interval, to convince our peers and to convince the community. That's two things. And then the role of simulation is both an opportunity and a challenge, as I said, because it is never accurate enough and it is never fast enough. Okay, I thank you.